Hello, in this video, let's discuss a little bit about how to size up gates and then talk about logical effort. We've looked at the RC model, which helps us look at transistors when they're switching, and we've looked at the Elmore delay model, which helps us find the delay in long RC trees. Now let's put these two together to look at the delays in complex logic gates. So we look at methods to design these gates for specific delay requirements, and I'll also introduce the concept of logical effort, and this will be used when we are going to be doing data path design, that is estimating the delay in a cascade of gates. So let's first begin with recalling sizing in an inverter. So let's assume that we have a technology in which the mobility of holes is half that of the electrons, and therefore we size up an inverter with the PMOS to be 2 times the size of the NMOS. Now if we assume that this inverter is driving a very large capacitive load, that is, in this case we can assume the capacitance at the output node is completely dominated by this external capacitance, then the pull up and the pull down delays are equal, and they're given by R times CL, where R is the resistance offered by this NMOS during the pull down transition or this PMOS during the pull up transition. And so when we design the inverter, we choose 2 for the PMOS and 1 for the NMOS because we've designed it such that the pull down resistance equals the pull up resistance. So the same logic will be used when we're going to design CMOS gates. We will size up the gates in such a way that in the worst case, the pull up and the pull down resistances are going to be equal. So when we design these CMOS gates, you'll realize that not all delays are equal. That is, certain transitions will be much faster than certain other transitions. And so it is important to estimate which is the worst case transition that will eventually limit the propagation delay of the gate. And then for that case, size up the transistors in such a way that pull down resistance or the pull up resistance is equal to that of this inverter. Now let's look at a stack of 2 NMOS transistors. So because they are connected in series, their equivalent resistances are going to show up in series. So suppose I want to size up these transistors such that the pull down resistance of this path is R. Then I know that each of these transistors are going to offer a resistance, and these two resistors are in series, so I'll size them up such that each transistor offers an R by 2 resistance, which means that I'll size up the NMOS to 2 times that of this inverter and the other NMOS to also 2 times that of the inverter. So by doing this, what I've essentially achieved is the net pull down resistance of this path of 2 NMOS transistors is essentially R. So now if I extend this to a stack of 3 NMOS transistors, then again to ensure that the net resistance in this stack is R, I'll size the transistors in such a way that every transistor contributes an R by 3 to the resistance, which means that each transistor will have a size of 3, that it is going to be 3 times as wide as the NMOS transistor in the inverter. Now if I look at a stack of a PMOS transistors, in the PMOS, right, the resistance of the PMOS is already twice that of the NMOS. And so if I have a stack of 2 PMOS transistors, I need to size them up in such a way that each of them provides a resistance of R by 2. Now since one PMOS transistor of size 2 provides a resistance of R, if I want an R by 2 resistance, then I need to size up the PMOS to twice that of the inverter, and so each PMOS in this stack of 2 PMOSs is sized up to size 4. Right? That ensures that the pull-up resistance of this path is R. Now let's extend this concept and look at sizing in the NAND 2 and the NOR 2 gates. So the NAND 2 gate consists of 2 NMOS transistors in series and 2 PMOS transistors in parallel. Now if you look at the pull down condition, pull down occurs only in one case when both A and B are 1, right? In which case the two NMOS transistors are going to be in series. Now I want the pull down resistance of this stack to be equal to that of this inverter shown here, and so therefore I'll size up the NMOS so that each NMOS transistor in this NAND 2 stack provides a resistance of R by 2. Now let's look at the PMOS, the pull-up stack. So the pull-up consists of two parallel paths, the PMOS A transistor and the PMOS B transistor. And so in the worst case, if you consider the worst case in pull-up, the worst case is going to be when only one of these transistors is supplying current to charge up this node. Right? The delay is going to be much shorter if both these transistors are supplying current to this node. So in the worst case, we'd assume only one of these transistors to be on. So we have to size them up in such a way that even when one of these transistors is on, the pull-up resistance is the same as that of the pull-up resistance in the inverter. Therefore, the size in the NAND 2, we're going to size up the NMOS transistors to be twice that of the inverter because they appear in series, and we're going to size up the PMOS transistors to be the same as that in the inverter, because in the worst case the pull-up in the NAND 2 gate looks just like the pull-up of an inverter. Now extending the same logic to a NOR 2 gate. In the NOR 2 gate again, there is only one pull-up condition, and that pull-up condition happens when both A and B are 0, and there are multiple pull-down conditions, but the worst case pull-down condition is going to occur when either A or B is 1. In the worst case, pull-down happens when one transistor is on. So the worst case pull-down looks like the inverter. The pull-up consists of two PMOSs which are connected in series, and so therefore I'm going to size up the NOR 2 gate as 4 in the PMOS and 1 in the NMOS. Now one thing I also want to draw your attention to is that if you look at the input capacitance, or if you look at the capacitance at this node A looking into the inverter, the net capacitance node A sees is 3C, 2C from the PMOS and 1C from the NMOS. Now if you look at the NAND 2 gate, the net capacitance seen by the input A is going to be 2C of the PMOS and 2C of the NMOS. The net capacitance seen by an input in the NAND 2 gate is much larger than what is seen by the inverter. And you'll see that this will be something that will be common across most of the complex logic gates. Now, just a note on the stacked transistors. Please remember that in stacked transistors, so the reason when we look at an NMOS stack like this, we size it up as 2 times. So when we do that, we're essentially assuming that both these transistors are operating identical to each other. So two things to keep in mind is, one, when both these nodes are at VDD, for example, when the gate of M2 is at VDD, the VGS of M2 is VDD. However, when you look at the gate of M1, when it is at VDD, its VGS is not going to be VDD, but it's going to be some voltage which is less than VDD, because there is going to be some drain to source voltage associated with M2. Secondly, if you short both the substrate contacts in this transistor, you're going to have a VT in M1 which might be different from the VT in M2. We'll have to equate the drive currents, but that doesn't necessarily translate to this looking like a transistor whose gate length is 2 times L, right? And the second thing you want to keep in mind is, remember, when we have velocity saturation present in the transistor, the effect of the gate length gets reduced. And so when you look at two transistors whose gate lengths are L and L, equating them to a transistor whose gate length of 2L gets even worse when velocity saturation is present in the picture. And so in reality, you'll see that the sizing of this transistor is going to be something less than 2 times, and how less it is going to be dependent on how velocity saturated these transistors are. But again, nevertheless, for these simple calculations, we'll continue to use the simple formula that assume that when we want to design a stack of transistors, we'll ensure that all the resistors are equal. So now let's look at sizing a 3-input NAND gate. So again, in the 3-input NAND gate, The worst case pull up is going to happen when either of these transistors, the PMOS transistors, is turned on. So in the worst case, the 3 input NAND gate for pull up looks similar to an inverter. So the PMOS is going to be sized similar to that of the inverter. Now if you look at the NMOS here, the NMOS consists of 3 transistors connected in series. So I will size up in such a way that each transistor corresponds to an R by 3 resistance, which means that I'll have to size up each of these NMOS transistors. And so the sizing eventually of the NAND 3 gate is going to be each NMOS with a size 3 and each PMOS with a size 2. Let's look at another gate, which is the AB plus CD complement gate. Now here, if you look at the pull-down network, the pull-down network consists of 2 paths in parallel, a path AB and a path CD. So in the worst case for pull-down, I see a stack of 2 transistors. So either AB is going to be 1 or CD is going to be 1. So when I'm going to size the NMOS transistors, in the worst case for pull-down, the pull-down is going to happen through a stack of 2 NMOS transistors in series. When we look at pull-up, now the pull-up again consists of C and D in parallel to A and B. So in the worst case of pull-up, the pull-up has to happen through 2 PMOS transistors connected in series. So the worst case pull-down is made up of 2 NMOSs connected in series. The worst case pull-up is made up of 2 PMOSs connected in series, and hence the sizing of this gate is going to be such that we size all the NMOS transistors to be twice that of the inverter, and we size all the PMOS transistors to be twice that of the inverter. So this is going to be the sizing such that the worst case pull down resistance is equal to the worst case pull up resistance. Using this sizing, let's try and calculate the delay in this gate using the RC delay model. So this is again a NAND 2 gate, in which case pull down occurs only when both inputs are 1. Now a note to remember is that if you look at series transistors consist of this common junction present here. So if you look at the stick diagram of this NAND 2 gate, you will see that you can share the source of A with the drain of B. And generally in old technologies, when you used to share this junction, the same N plus junction between these two, the capacitance associated with this node, instead of it being associated due to 2 junctions, you associate it only with 1 junction. So generally shared source drain capacitances tended to be smaller. But what we'll do in this discussion and subsequent slides, we'll assume that capacitance at the shared node of transistors is going to be exactly the same as would have happened if this source drain was not shared. This way we keep the analysis simple. But please keep in mind that in reality, when you have such structures, you might end up finding that the capacitance at this node is less than what you had estimated. So now let's find out what the various capacitors at the nodes are. So let's look at the output node. At the output node, I have the drain capacitance of the PMOS A, the drain capacitance of PMOS B, both of which contribute 2C and 2C, and the drain capacitance of the NMOS A, which also contributes 2C. So the net capacitance at this node is 2 plus 2 plus 2, which is 6C. Similarly, the net capacitance at the shared node between A and B is going to be the source capacitance of A and the drain capacitance of B, each of which is 2C and 2C, giving you a 4C capacitor. Now there are 2 other capacitors in this network. One is the capacitance at the sources of PMOS A and B, each of which give a 2C, giving a 4C capacitance at this node. And similarly, you have another capacitance at the source of the NMOS B, which is a 2C capacitor. Now both this 4C and 2C capacitors are essentially connected to power supplies, and they do not have any change in charge. So basically these two capacitors are neither getting charged or discharged. So we don't have to worry about them during delay calculations. So in delay calculations, we'll worry about only these 2 capacitors that are present in the circuit. So let's calculate the delay using the RC delay model. So let's assume we want to find the falling delay of the circuit. That is, we want to find the delay when B is 1 and A switches from 0 to 1. Initially A is 0, B is 1, at which point the output is at a VDD, right? So this PMOS A is shorted, this node is pulled up to VDD. Because this NMOS is open, there is no connection between the output node and ground. Now when A transitions from 0 to 1, I shut off this PMOS transistor, I turn on this NMOS transistor, and so what happens is now I have a transistor which is essentially pulling down the output from VDD to 0. So in that case, I can think about it looking like a resistor of R by 2 and R by 2 in series, which is essentially R, and R is being connected to a 6C capacitor, so the pull down delay is 6 times RC. Similarly, if you want to find the rising delay from 1 1 to 0 1, that is when A switches back from 1 to 0, in that case again what's going to happen is when A switches from 1 to 0, I turn off this NMOS, so this path becomes open. This A turns on, leading to a charge up of the 6C capacitor through a resistance R, leading to a rise time of 6RC. So in this case, you have the falling delay and the rising delay both to be 6RC. And this is by design because in the worst case, we have planned for the pull-up resistance to be equal to the pull-down resistance. Now, interesting things happen when we have these transistor stacks because then there is this capacitance that we need to worry about. So let's assume that we now have A to be 1 and B transitions from 0 to 1. Let's look at the case when the input is A is equal to 1 and B is equal to 0. So when A is equal to 1, this PMOS is turned off. B is equal to 0. So this PMOS charges up the 6C capacitor. But because A is also 1, this transistor is on. So the PMOS here is charging up both the 6C capacitor and the 4C capacitor, right? This NMOS transistor which is connected to input B is turned off, so there is no current flowing to ground. But because A is on, this 4C capacitor also gets charged up to VDD. So now when B goes from 0 to 1, when this switch is turned on, this NMOS B switch is turned on and this switch is turned off, I now have to discharge the 6C capacitor and also have to discharge the 4C capacitor, right? So therefore, my discharge circuit looks something like a 6C capacitor connected to a transistor size 2, hence R by 2, and then I have a 4C capacitor and then another transistor whose resistance is R by 2. Now I want to find the Elmore delay for the falling transition, going to be the delay between S and 2, right? And when I use the Elmore delay, it's going to be R by 2 into 4C plus R by 2 plus R by 2 into 6C, which works out to be 8RC. So what you see here is that this delay is going to be longer than the 6RC that we had estimated previously. And that is because of this 4C capacitor which is coming into play, which is causing the delay to increase. And so what you need to keep in mind is generally when we look at complex gates, timing in the gate is input sensitive. And so many a times we'll have a bunch of delays that will be associated with the gate, and the delays depend on what the input transition is going to be. So conservatively we take the longest delay to mean the propagation delay of a given gate. Now similarly we can use the logic to look at the delays in a NOR2 gate. Now in a NOR2 gate the issue is more severe because the PMOS transistors are wider, and therefore if I assume that the shared source drain do not reduce capacitance, I have a much larger capacitance at this shared node than I actually have at the output node of the gate. And so therefore what you'd see is when you take this capacitor into account, when we consider the charging and discharging of this capacitor, you end up seeing that the delays associated with that tend to be much longer than the nominal delays that are associated with this gate. And so you have delays ranging from 6RC all the way to 18 RC in this case, right? If I'm going to be conservative, I'll say the propagation delay of this NOR to gate is 18 RC. If I have to be very careful, then based on the inputs, I will use those particular delays to measure the delay of the gate. So many times for delays, we talk about contamination delay and propagation delay. And so in this case, given the delays we have and given the 4 transitions we have, we'll say that the contamination delay of this gate is 6 RC and the propagation delay of this gate is 18 RC. Now let's look at the NAND 3 gate. So in the NAND 3 gate again, we have the 9C capacitor at the output, and that comes about because of 3 PMOS drains, each of size 2. So it's 2C plus 2C plus 2C, which is 6C, and an additional 3C from the drain of the NMOS transistor, giving you a 9C capacitor at the output node. And then you have a 6C capacitance at this intermediate nodes. So if we neglect the impact of this transistors at the stacks, then essentially the delay of this gate, because we have sized it up in such a way that the worst case pull-up delay is equal to the worst case pull-down delay, nominally I'll say that the delays of this gate are 9 RC. What we see is that these capacitors kick in when we have this gate turned on but the bottom gates switching, right? So ideally, if you have to design a gate like this, and if you know something about the signals, what we normally do is we ensure that the late arriving signals are placed closest to the output node. So in this case, if I were to be careful, I'll assume that C is the signal that arrives the earliest, A is the signal that arrives the latest. And so therefore, by ensuring this condition where the earlier signal has already arrived at the NMOS connected to the ground, I ensure that this gate shows limited effect due to these intermediate charging capacitors. So that's generally the rule of thumb, that late arriving inputs are generally placed closer to the output node. Now let's talk about the impact of fan out of this NAND 2 gate. So let's consider I have the smallest NAND 2 gate, and the NAND 2 gate is going to be sized in the following fashion. The PMOS transistors are sized to 2, the NMOS transistors are also sized to 2. Again, shown here is the smallest inverter in this technology. So let's assume that we have this NAND 2 gate driving another NAND 2 gate which is sized m times larger than this gate, which means that its transistor sizing is going to be 2m, 2m, 2m and 2m. And to keep our analysis simple, we'll assume that the delay or the parasitic delay at this node is completely dominated only by whatever is the parasitic capacitance at the output node. That is, I won't worry about the capacitance at the stacked node. So now if I look at the total capacitance at this node, the total capacitance at this node is due to this intrinsic capacitance of the first gate and the gate capacitance or the fan out capacitance associated with the next gate. So the intrinsic capacitance of the first gate is given by 2C plus 2C plus 2C. So this 6C is the intrinsic capacitance of the first gate. Now the fan out capacitance at this node is given by the input capacitance of the next gate, which is going to be as 2MC because of the PMOS and 2MC because of the NMOS. And so therefore our net capacitance at the output is going to be 4M plus 6C. Right? So as this M increases, as I make the load gate larger and larger, I'm going to have a larger capacitance appearing at the output of the first gate. Now again, we have designed this gate in such a way that its worst case pull up resistance is equal to its worst case pull down resistance, and in both these cases the resistance is R. So I can talk about the falling and the rising delays, or the pull up and the pull down delays, as 4M plus 6 into RC. Now to eliminate the impact of RC and just talk about logic per se, we will talk about normalized delays. That is, we'll convert all these delays into multiples of tau inverter. So when I divide these delays by the delay of the inverter, what I get is the normalized delay of this gate is given by 4 by 3 into M plus 2. M again is the fan out associated with this gate. 2 is the parasitic delay of this gate. So what we see is that the parasitic delay of this gate is twice that of the inverter. Remember, in an inverter, the parasitic delay is 1. So if I plot this delay as a function of the fan out, I see a straight line here. So this is known as a linear delay model, where the delay increases linearly with respect to fan out. Shown here is also the delay model for an inverter of the same technology, and what you see here is that the inverter shows a passive delay of 1 and then a delay that increases proportional to the fan out. NAND 2, we see that its parasitic delay is higher and the slope of increase of the NAND 2 seems to be larger than that of the inverter. Okay. Now let's look at a NOR 2 gate. Now in a NOR 2 gate, again, this is the nominal inverter in the technology. So in a NOR 2 gate, I have a small gate driving another similar gate which is sized m times larger than this gate. So again, if I look at the total capacitance at this node, the total capacitance at this node is going to be the internal capacitance of 1 plus the gate capacitance of the m gate. So the capacitance at the output of gate 1 is 4C to the PMOS and 1C and 1C because of the NMOS. So that is 4 plus 1 plus 1, which is 6C. And then the input capacitance at each node is going to be 4M plus 1N. So it is 4 plus 1 into MC or 5M plus 6C. Again, we have sized this NOR 2 such that the pull up resistance is equal to the worst case pull down resistance equal to that of the inverter. And so our pull up and pull down delays are nominally given by 5M plus 6 into RC. And if you look at the normalized delays, they are given by 5 by 3M plus 2. Right? So now if I plot this back on the previous graph, what I see is the following. Again, the NOR 2 seems to again have the same parasitic delay as the NAND 2, but NOR 2 seems to be slower than NAND 2. That is, for the same fan out, NOR 2 seems to have a higher delay than the NAND 2 gate, and we see that both these gates are slower than the inverter. And if you look at that, that is characterized by the slope of this graph. So you see that the slope of the graph for the inverter, that is the delay versus fan out, the slope is 1. Whereas if you go to the NAND 2 and the NOR 2 gate, you see that the slope increases. And this slope is nothing but the logical effort of the gate. So what we see is that complex logic gates are slower than the inverter. So to bring in the formal definition of logical effort, we know that the load capacitance of any gate has two components. One is the intrinsic capacitance of the gate, and the second is the fan out capacitance of the gate or the extrinsic capacitance. Now in terms of tau inverter, if I look at the normalized delay of the gate, then I see that the normalized delay of the gate consists of two parts. One is the parasitic delay, that is the delay associated when I do not have any load attached to the gate, and this is represented by the letter P. The other delay represented by the letter F is the effort delay, and that depends on the fan out of the gate and also its complexity. So if I increase the fan out, this component of the delay increases, whereas this component stays the same. Now this effort delay F is sometimes given as a ratio of G times H. And what is H? H is known as the electrical effort of the gate, or rather the ratio of the output capacitance to the input capacitance. Right, now what is the output capacitance? As we increase the output capacitance, we expect the delay to increase. So the electrical effort is increasing. Input capacitance is measure of the width of the transistors which are driving the gate. Right? So if I have a larger input capacitance, it means that I have larger transistors, so I have more current to charge or discharge the gates. Hence the electrical effort, you're trying to compare what is the net capacitance I have to charge or discharge, and you're comparing it to the width of the transistor that is charging or discharging that capacitance. Now this G, this prefactor to the electrical effort, This changes depending on the kind of gate you're using, right? So we looked in the previous case. If you used a NOR gate, for the same fan out, the NOR gate was slower than the NAND gate. And that degree of how slow it is or how fast it is clubbed in this term G, and this G is known as the logical effort of the gate. Or in other words, it's nothing but the cost of doing business with respect to delay when you're using this gate in a data path. If I now look at delay as a function of fan out, normally I see that delay versus fan out is a straight line in almost all gates using the RC delay model. And at any point, the delay in the gate has two components. One is the parasitic delay, which is independent of fan out. The other is the effort delay, and that depends on the actual fan out that the gate is driving. It's important because what we want to know is many a times we use gates other than inverters in a data path, right? And so what happens is a larger gate is going to give you more delay for the same fan out. And so when you're trying to compare different gates, it becomes difficult to understand the concept of delay. And so what we do is logical effort kind of helps us normalize any gate to that of a common inverter. So by saying that the logical effort of a NAND 2 gate is 4 by 3, what I'm essentially saying is that the NAND gate has a 33% higher delay when compared to an inverter for the same fan out. So we see that complex gates generally tend to have this larger logical effort and hence a larger effort delay. Additionally, we see that complex gates also have larger parasitic delays. So another way to look at logical effort sometimes is to measure the delay in the gate and normalize it to the delay in the inverter of the technology. So to measure the logical effort of any gate, what we do is we design the gate such that its drive resistance or its pull up or pull down resistance is matched to that of the inverter. In that case, then the ratio of the input capacitance of that gate to the input capacitance of the inverter is the logical effort. If you look at the two input NAND gate, the two input NAND gate had an NMOS stack which has of size 2 and 2, and then a PMOS stack which was also sized 2, right? And so if you look at this resistance, the pull down resistance of this stack is R, the pull up resistance is also R, and so therefore the input capacitance of this gate is 4C. I compare that to the input capacitance of an inverter, which is 3C, and so therefore the logical effort of a NAND 2 gate is given by 4C by 3C or 4 by 3, which is what we saw in the slope of the graph when we looked at delay versus fan out. And I could do this because I've designed this gate in such a way that its pull up and pull down are equal to that of the inverter. To conclude, design of complex gates generally involves designing the transistors to achieve minimum delay. Now, one way to do that, which is what we normally use, is to ensure that the pull-up resistance and the pull-down resistance, in worst case, matches that of an inverter. That way, we ensure that at least one part of the delay is minimized. We use the method of logical effort to normalize delays across multiple logic gates, and this becomes very useful when we look at design of a data path or when we try to minimize the design so that we can achieve minimum delay, which we will look at in subsequent lectures.